What's up, everybody? This is Wallace from A3Academy. Today's topic is going to be on phase diagrams. It's going to be really short. Today's kind of an interesting day for me. I just went to Ethiopia to attend the funeral of my friend Pete, and then it turned out that Pete was alive. So yeah, he played a prank on me, but little does Pete know that I have actually sold off our A3Academy company car. He really loves that car, so he's going to be really angry once he gets back to the studio. But in the meantime, phase diagrams. Let's get started. So what do phase diagrams do? They help you out to find the phase of matter or the state of matter of a material. And by phase of matter, I mean solid, liquid, gas, those kinds. So the phase of the matter of a material depends on two major factors. Those two factors are temperature and pressure of the material in question. So if we know the temperature and pressure, we can use a phase diagram to help us figure out the phase of matter of the material. And this is what a phase diagram looks like. This isn't an actual phase diagram. I actually made this up completely. Later on in the podcast, we will look at real phase diagrams of real compounds. As you can see, it has pressure on one axis, temperature on the other. Notice these 2 points here. The first point, and probably the most important point you need to know, is the critical point right there. If you draw a horizontal and vertical line to the critical point, you will end up with these 5 major sections. And each one of these sections corresponds to a different phase of matter. The solid phase is when you have all of your atoms and molecules tightly packed together. Then you have your liquid phase, when the atoms are a little more freely moving but still kind of packed together. Then you have the vapor and gas phases, which are when the molecules are very spaced apart and flying around at very high speeds. The difference between a vapor and a gas is literally that a vapor is below the critical temperature and a gas is above the critical temperature at the critical point. And then the last section we have is what's called a supercritical fluid. This is the point where you can no longer tell the difference between a liquid and a gas. It's just one fluid material under high pressure and high temperature. So let's analyze this a bit more. So if you wanted to find the phase of matter of a material, all you would have to do is find a point on the graph that corresponds to the temperature and pressure that you're given, and find out what section of the graph it's on. So suppose that using this phase diagram, I want to find out the phase of matter of this mystery compound when it is at a temperature of 400 Kelvin and a pressure of 30 atmospheres. Well, it is as simple as finding the point on the graph and knowing what section it's in. In this case, it's the liquid section. Therefore, at 400 Kelvin and 30 atmospheres, our material will be liquid. Now, the same material at 100 kelvins and 50 atmospheres pressure, once again, all you have to do is find the point on the graph, and in this case, it's a solid because it's in the solid region. What about at 450 kelvins and 10 atmospheres? Well, once again, we draw the point. It's a vapor. Notice that the temperature is actually lower than the critical point temperature, so it's a vapor. Now we've got this other point on the graph called a triple point, and that's where 3 phases of matter all meet in the same place and are at equilibrium. And in the case of this graph, this triple point is where solids, liquids, and vapors all intersect with each other. So this is what's called the solid, liquid, vapor triple point. And if you were to take a material and put it at its triple point, some cool stuff would happen. For example, this is tert-butyl alcohol. It is boiling and freezing at the same time. So that's pretty cool what you can do at the triple point. So far we've been looking at this sample, completely made up phase diagram. Now let's take a look at some real phase diagrams of some real materials. So this first one is of H2O or water. This is what the phase diagram looks like. Just like in any phase diagram, you have the critical point on the top right. You can draw a horizontal and vertical line, and you will be able to divide the phase diagram into the 5 sections that we discussed earlier. But H2O's phase diagram is actually very, very strange. And it is strange because this line right here has a negative slope. This line is the equilibrium line between the solid state and the liquid state. And since its slope is negative, that would mean that as the pressure increases, water is more likely to be a liquid. That doesn't make sense because if we took a lot of molecules and used pressure to squeeze them all together, they would become tightly packed and that would be a solid, right? Because of all the hydrogen bonds that are between H2O molecules in ice or solid water, these water molecules are held at a distance from each other. So if we were to apply more pressure to a solid block of ice, we would break the hydrogen bonds in the ice, causing all of these water molecules to slip over each other. And that's when we have a liquid. So again, notice that the equilibrium line in CO2 has a positive slope. That if we had a block of solid CO2, also known as dry ice, and we compressed it more and more, it'll always be a solid. But with water and its hydrogen bonds, that's not always the case. So that's one of the reasons that the phase diagram of water is actually different than most phase diagrams. So let's get into some real problems about phases of matter. First question, what is the state of matter of water at 589 Kelvin and 220 atmospheres? So to solve the problem, all you have to do is pull up the phase diagram for water, right? Find the point on the graph, and you have a liquid in this case. Next question, what is the state of matter of CO2 at 529 Kelvin and 35 atmospheres? Once again, we take a look at the graph. Notice that the temperature is higher than the critical point, but the pressure is lower. Therefore, it's a gas. And one last question, what is the state of matter of water at 178 Kelvin and 483 atmospheres? Once again, to figure that out, all you have to do is take a look at the graph. But notice that this time, the point isn't in one of the sections. It's actually on the line. When the point is on the line between two phases of matter, then those two phases are in equilibrium in the material. Since in this case, the two phases are liquid and vapor, at this certain temperature and pressure, these two phases will be in equilibrium. This is known as the liquid-vapor equilibrium. And water molecules are continually switching between liquid and vapor at pretty much an equal rate. So with that having been said, that's all you need to know about phase diagrams and how they work. And we're pretty much done for today. I'm Wallace from A3 Academy, and as always, the more you know, the better you are.